Okay, so this will be running Quake 3 Arena with another custom experimental software OpenGL implementation. So yeah, this is basically the implementation I was developing for my BGX2 project, which currently can sort of run GLQuake. Not particularly quickly, but it does run it on BGX2, but it also works on a native Windows build here, which is what I'll be showing off. The title, or the opening video issue there also appears with the native hardware build, so I'm suspecting it's probably a bug somewhere else. But I'll go to this map, since this is one of the more graphically fancy maps. Getting these grates working was a fair bit of debugging, because these combine basically multiple features at the same time, including alpha testing and blending. So I had to support blended alpha test modes to make this work. So yeah, great. Yeah, the jump pads and also some other effects depended on the use of basically ST clamping, or clamping the ST coordinates, which is a little bit more expensive for a software implementation. Yeah, for a software implementation. Initially, I tried clamping it per pixel, but that was expensive. So instead, I ended up switching to a span clipping and clamping approach. With the span clipping, with the span clipping approach, instead of needing a separate version of the span function, which performs clamping and also to do the logic for clamping for each pixel, it will instead basically classify parts of the span as either inside or outside the texture, and split the span if needed, and clamp the coordinates, which sort of works, and it's a little bit faster than the per pixel clamping. These doors were also a bit of debugging as well. Mostly trying to figure out how to make the blend function work correctly. But not sure if those are supposed to be mirrors or TVs or what. But that effect does seem to be consistent with the they're consistent with the hardware implementation, so whatever it is, it seems to be working. Yep, also overhead lights. They involve some extra funkiness as well, namely they're drawn with the depth rights disabled. So yeah, I feel like if the depth buffer is still written with that effect, then it causes pretty obvious artifacts. But yeah, so another combination of features. The reason I mentioned so many like special cases involving blending and so on is because this particular implementation, it effectively special cases most of the different span types. So this here is actually a single threaded implementation, and contrary to usual expectations on the x86 build here, this is not using sim. This is basically just single threaded scalar code. But partially the reason for that is this is being optimized more for the capabilities of the BJX2 ISA than to be necessarily a good x86 implementation. But as far as performance goes on x86, it does seem to be within the realm of plausible for a single thread, mostly scalar code implementation. The BJX2 implementation does rely more heavily on simmed. However, the simmed capabilities of BJX2 don't map like particularly closely to those of SSE or similar, so it's not quite one-to-one. And in plain C, also it's mostly limited to fairly generic scalar types. However, this does make fairly extensive use of 64-bit integer types, so that is kind of a concession of sorts. Whether or not using 64-bit integers can be counted as a type of simmed or not is subject to interpretation. Sort of got distracted there and didn't realize that was, jumping off into the void there. So yeah, yeah, at a higher resolution like 960 by 720 or similar, this is kind of a little bit unpleasantly laggy, but at 640 by 480, it's reasonably acceptable. At least, in light map mode, it's actually faster in Vertex mode. I went to a Q3 DM12 here because this is the map that seems to have a wide variety of different special effects going on. So, so yeah, the sky also works. It can be noted also that this implementation is not using perspective correct texture mapping, but rather it's relying on subdivision. So slight texture rippling may be noticeable. So yeah, slight texture rippling may be noticeable in some cases, but it's more noticeable at lower resolutions, like 320 by 200. At 640 by 480, the amount of subdivision does seem to fairly notably reduce the amount of rippling. I switched it over to Vertex light mode, which is, yeah, I switched it over to Vertex light mode, which is a little less fancy, but it is computationally cheaper and faster. For anything that I'm running on VGX2, I'm generally using a Vertex light mode. I sort of added a similar mode to Quake 1, which is basically my main hope for, like, you know, trying to get it semi-usable. to. This map had another interesting effect on it, but I'm not sure if it works. Not sure if the effect works in Vertex light mode, because I've not tested it. It appears it does. So, yeah, I can see through this portal in Vertex light mode. Though that effect's a little different. In the other mode, it sort of goes into a fog when you get further away, whereas here it just sort of stops working. So yeah, as noted, this is working mostly by a lot of fairly extensive use of spatial casing. So for most of the basic blending modes, which would includes the or the non-alpha blended modes and also the alpha blended modes and so on, or the basic ones. The span drawing logic is pretty much hard-coded with a different span function for each special case. So, wait, clicked on the wrong thing. So, this one is for blended spans. About, almost 900 lines of C code there. And another C function of span codes. This is for the this is for a lot of the fixed blend modes for similar. As noted, there is a bilinear interpolation, which can be noted. It is being rendered as using bilinear filtering rather than using nearest filtering. So it's kind of what this logic looks like. But so bunch of span functions. Similar logic copy pasted a bunch of times with slight differences. While that may seem like this may seem like pretty terrible coding practices, it's done this way mostly because this is about the only real way to try to get acceptable performance in this case. So for example, this one here, it's alpha tested, then color modulation, which is pretty much all of them, and text, which basically means it's a plain texture map, then which is Morton order, and ZT for Z-test. So that's basically the naming convention. And so it's be seen the Morton is here, then it basically grabs a pixel, unpacks it, then does an emulated simmed multiply, which is not actually a simmed multiply on x86, but close enough, and then it repacks it, and if the z-test is correct, well, a z-test and an alpha test, then it stores a pixel. This one is bilinear filtered, so you can see it fetches several pixels, then it bilinear interpolates them, then it, does the thin stuff. Alpha blended case, which is, well, similar, hard-coded alpha blend. A lot of the more general cases, they'll not do it this way. They'll be more generic. So I can find it. Yep. So this would be, yeah, ignoring the F0 sections. So this one is a Z alpha test modulated bilinear, and then this one's using the UTX2 texture compression, also Morton, and also Z test. So, but yeah, as opposed to this case, which was an older or hard-coded Z test, which is just sort of lingering on in a vestigial form. But so in this case, yeah, the indexing and Morton are still hard-coded, and it still fetches the pixels and does a bilinear filter. But then what happens is it basically modulates the color and does the blend. And this is what's special about these functions, is that they use the like a ZA test function, which combines the Z test and an alpha test, and can also implement a few other special effects in a semi-generic way, but can't really use this style of case for everything, because well, function calls aren't free, so this particular approach is a little bit slower than the use of, well, some of this stuff over here. Particularly on the slow BGX2 processor, which you really don't want to be throwing a random function call in the middle of the blend loop. And this is, well, this is one of the versions of this logic, but not necessarily the most efficient one. Hold on. Okay, yeah, I think it's this one. Yeah. So yeah, in this case, here's the this is the inner loop for the main part of the span drawing thing, which I was able to get into a reasonably compact form. This is we're basically modulated using the UTX2 format in Morton, and ZB basically means both Z test and C buffer. So in this case, it also performs the depth right. So, well, yeah, this is a simpler case. It does color modulation and texture compression, but yeah, yeah, it does color modulation and texture compression, but it's, you know, not doing. This one doesn't do bilinear, but this is the nearest neighbor case. But either way, it is, well, the main loop is reasonably compact, where this little vertical bar basically indicates which instructions are being run in parallel and stuff. And I had jostled around the instructions to get a reasonable amount in parallel, but it's still not quite ideal. For example, in this case, a load is performed here, and the result is used immediately in the next instruction, which will incur like an interlock delay. But there wasn't really a good way around that, because ideally you'd put the load a few cycles before where it's used, but sadly there wasn't really a good way to pull that off in this case, so there is an interlock delay, but other than that, as can be noted, it's a reasonably compact span drawing loop, and there's no function calls or anything like that, so that's kind of how I'm at least attempting to get acceptable performance out of this stuff on such a slow processor. And in x86 land, it's, well, yeah, pretty much all this stuff's being faked with function calls, so it's somewhat less efficient. And as noted, the way BGX2 does SIMD doesn't really map that closely with SSC, or with how SSE does things, so for a lot of this I didn't really bother. It does sort of work as noted here, because well, my Ryzen 7 CPU is roughly about 80 times the clock speed, so it can handle it. Theoretically, it could probably be made, like, you know, a bit faster on x86, say if SSE were used effectively, or if this were multi-threaded, but generally I consider this to be acceptable results for a single-threaded rasterizer. So yeah, the x86, or for testing, I've been running Quake3 on x86, but here, oh, wrong one. Yeah, here can use an emulator. Let's throw it into JIT mode so it's faster, but this is, you know, way faster than the actual FPGA core is, so it's not particularly realistic, but will give an idea. So yeah, despite being run unrealistically fast, this can be noted. Yeah, GLQuake does sort of work. And this at least gives an idea what it looks like, even if it's, well, you know, a lot higher frame rates. Got caught on the door. Yeah. So as can be noted, yeah, the texture filtering is, well, doing its fuzzy texture thing, and also GLQuake is, you know, doing its GLQuake thing, including the sky effect and so on. The texture rippling and other artifacts are a little bit worse at this resolution because it's internally rendering at 320 by 200, which is quite a bit lower than 640 by 480. But, curious, but yeah. There are some issues with Z fighting and so on because I am using a 16-bit Z buffer, which is not the highest in Z buffer depths. A 24-bit Z buffer would have been preferable, but the issue is a BGX2 core is seriously limited by memory bandwidth, so spending roughly 4 bytes or so for each Z buffer index would have been undesirable. Similarly, it's using a 16-bit color depth for rendering, which is not particularly the highest end in color depths. It's effectively high color, so yeah. Actually, it's a more funky format than that. It's actually like, you know, a format that's either RGB 555 or RGB 444A3, depending on one of the bits. But that was a reasonable compromise in some areas. But yeah, doesn't necessarily give the highest color fidelity or so on, but generally looks like something. Annoyingly, the fast.jet compiled mode doesn't give profile information or anything like that, so yeah. It also did give 17 frames per second, but that's a bit, well, unrealistically fast. But I just did it this way so that it wasn't painfully slow, because well, low single digit frame rates aren't exactly fun, so yeah, so what's going on there. But more work will continue on this, but so far it seems like semi-viable. It is possible I could port Quake 3 over to BJX2 natively, but not done so quite as of yet, and as can be noted, I don't really expect it to give all that great of performance on the actual FPGA version, so it's debatable. But a Quake 3 port is looking like it could be technically possible to pull off, even if it would be pretty much unplayably slow. But yeah. Trying to think of if there's anything more I have to say on this. Yeah, I think I've probably said what needs to be said on this. So, guess I'll know later whether or not I failed to mention something, but yeah. All for now.